So it's a great pleasure to have Professor Martin Bojowald in the 31st QASTM seminar. Uh, I don't need to give a big introduction to the speaker, but those who don't know him, just for them and for all the students, like he at present is working as a faculty member in the physics department of the Penn State University, and he's also associated with the Institute for Gravitation and Cosmos, which is also the part of the Penn State University. Before joining Penn State, he was at Max Planck Institute for Gravitational Physics, Potsdam, where I am right now, for the 2 years, 2003 and up to 2005. And his working area is physical cosmology, loop quantum gravity, and loop quantum cosmology. And today he is going to speak about some understanding of quantum models of space-time. So Martin, thank you very much for agreeing to give this talk and your time in this pandemic time. And so you are the 31st speaker of this series, and we are welcoming you virtually from Potsdam. You can start.
Thank you very much. Thank you for the invitation. Yeah, I'll talk about quantum models of space and time. Didn't put a hyphen in there because I will speak about space and time separately. Of course, it's important to combine them and make sure it's covariant, but I won't have much of a chance to talk about this. So first, brief introduction. So most of you know this. We do have a few expectations for quantum gravity, and the most basic ones are based on dimensional arguments. So the Planck length, which is very tiny, the Planck mass, which doesn't really sound very extreme, but then as the mass of a single elementary particle, it would be huge. And so is the Planck density. So we don't expect quantum gravity to be urgently relevant for observations, but all this is based on dimensional arguments, and they can easily fail when there are several parameters. An example would be atomic physics, where we can use dimensional arguments to derive the Bohr radius using the electron mass, charge, and h bar. And we get pretty close, up to a factor of 2. But if we try this with uranium, where we have many constituents, a lot of electrons, there's a large dimensionless number. And unless we have a good theory that tells us whether we should multiply by that number or divide by it, we don't get a good estimate. So in quantum gravity, we might also expect large dimensionless numbers if there's spatial or space-time discreteness, for instance. There would be a large number of building blocks, and we have to know how to put the numbers into equations. So we need a good understanding of quantum gravity before we can even make predictions. We don't really have a good understanding yet. But there are simple models which can at least tell us something about space and time, which is not just based on dimensional arguments. And they're still useful, even though they're simplified. So I'll start with the minisuperspace models, and most of my talk will be in this setting, but I'll explain how one can try to go beyond them. So the idea here is to use just quantum mechanics to describe space, which is assumed to be homogeneous, so there's no spatial variations. And that means there's a finite number of degrees of freedom. So the line element looks like this. They're just time-dependent functions, and space and time are clearly separated. So except for modified dynamics, it is really just like quantum mechanics when we quantize these functions. There are a few fundamental simplifications. Gauge freedom is much more restricted than in full gravity. The only transformations that we can do here, which preserve the form of the metric, are time reparameterizations, or maybe some spatial transformations, but That's usually Euclidean or rotation. That's pretty well understood. The only non-trivial transformation are time reparameterization. So instead of t, we can use any function t prime of t, at least if it's monotonic. But that can easily be fixed by a simple gauge choice using proper time, for instance.
So Martin, one question, yeah. Sorry. Why we start with this homogeneous space assumption for mini superspace models?
Oh, that's basically a definition of mini. So mini refers to usually finitely many degrees of freedom.
Okay.
So as soon as you have any spatial variation, it will be infinite dimensional. There might still be finitely many physical degrees of freedom, but before you impose constraints and equations, any model with spatial variation has an infinite number of degrees of freedom. So just by definition, that's what we call mini superspace models. Okay. Okay. And that's the main set of examples that I'll be talking about. So we have these, that's why we just have these time reparameterizations, because anything that mixes space and time would introduce spatial variations, and then the functions look very different. There are almost no spatial transformations or deformations, except one will be latest changing the total scale. If we have, it's easier to see how that happens if we have spatially flat models, then we just have the scale factor in QAB. And the scale factor can be multiplied by any non-zero, or say positive constant, which is a transformation. And we'll see that this actually is very useful, even though it's almost trivial in classical cosmology. So these are simplifications. They're clearly disadvantages. It's uncontrolled as an approximation to some full theory. Even if we knew any full theory of quantum gravity, it would be very difficult, probably impossible to show that mini superspace models are any approximation, because we are explicitly violating uncertainty relations. Because if we try to embed these homogeneous models in an inhomogeneous setting, then if it's quantized, we would have to set the fluctuation of fields and their momenta equal to 0 to have this homogeneous metric at one time and preserved in time. So we have to violate condition, and so it's not really going to be there's no embedding of many superspace models in a full theory, and the way it's usually constructed, there's no controlled approximation, because we first make this classical assumption about homogeneous space and then quantize the finitely many functions that appear. So it's not a construction within a quantum theory where one could try to find good approximations. So that's one thing which I'll be able to weaken a little bit later on. So one can, at least in, again, model systems, one can see how one could define a neighborhood or an expansion around these models. The second disadvantage is we have no direct handle on space-time structure, particularly after it's quantized. We just have these separate spatial and time transformations. We cannot perform local boosts because this would not preserve the form of the line element. And so in canonical language, which is what I will mostly use in this talk, we have simple time translations with constant time displacements in. H is, those of you who are not familiar with the canonical formulation, H is some kind of Hamiltonian, like a local version. And in the full theory, we have position-dependent time translations, and so that's a much more complicated situation, also concerning the algebra using Poisson brackets of these constraints, or Hamiltonians. It's very restricted, but it turns out there are still many subtleties in this mini superspace setting which tell us important lessons about quantizing space and time. So a few details, again, probably familiar to most of you, just to introduce some notation and see where different transformations come from. So we have the Friedmann equation. with the generic time coordinate here. So n, it's just the same n as in this line element here. We have proper time, n is just equal to 1, and then the dot would be derived by proper time. If it's a generic time coordinate, then there's this n function in there. And here, more specifically, this homogeneous metric for the 3 different choices of positive, 0, and negative curvature, depending on this k parameter. So this first function here, n, is really completely arbitrary. There's no observational information related to it. It's just strictly related to the choice of the time coordinate. So one can see this easily. If we have 2 different functions, both positive and tilde, then we can just integrate this relationship. It should describe the same line element. So these 2 differentials should be the same. And because there's both positive, we can integrate this relationship and get a monotonic function d tilde depending on t. And that's our coordinate transformation. So by a coordinate transformation, we can always eliminate any n function or map it to any other choice. And then the second term here, there's another time-dependent function with a scale factor, and that's more important. It appears in the Friedmann equation, so clearly something about it is observable. But not as a full function, but only as some kind of expansion rate, as in this case, because we can change spatial coordinates, rescale them, and this will also rescale the scale factor. So there's a little bit about transformations in this restricted setting, and we'll exploit this as much as possible to learn something about space-time. Question?
Yeah, so in the previous slide, yeah, when we write the FRW metric in the presence of the lapse function, can we say that this is kind of perturbation along the time direction? Because like usually it is minus dt squared. Now you are putting some time function. The similar kind of thing we also do during the ADM type of formalism. There we actually perturb the space part also, but here only the time part you are considering. So you can say that?
Right, here it's restricted to be time dependent.
Yeah.
It's by this homogeneity assumption.
Yeah.
And so we will, if we apply ADM here, we get a restricted set of constraints. We get only one constraint, one Hamiltonian constraint, and this is just completely equivalent to the Friedmann equation.
Okay.
So it's a much simpler situation in terms of canonical analysis.
Yeah. Okay. And
just another example, if you use n equal to a, you get conformal time. So these are the most common time choices. That's a little bit about deriving the Friedmann equation, first from an action principle, and then later on the next few slides I'll do canonical analysis. Again, that's something most of you have seen, but usually there's a factor V0 here, which I highlighted in red, which is usually ignored or set equal to 1. So in this derivation, we start with a completely general Einstein-Hilbert action. And we insert the Ricci scalar that corresponds to these line elements here. So it depends on n, which also is usually equal to 1, so it could be simplified. But I'll leave this free. And the second new parameter is this V0, because if we initially have a 4-dimensional integration, so time and space, because it's homogeneous, there's no spatial variation here, or, well, if there's curvature, there's still spatial variation in G and R, but it's very specific. We can always explicitly integrate this. And what we get is a simple factor, which is the volume of a region in which we're evaluating the action, a spatial region. So if we have 0 curvature, space might well be infinite, so we would have to pick a finite region. Doesn't really matter because it's homogeneous anyway, so it's the same everywhere. So classically, we can always just choose some region. We get a number which depends on the region, but in all the physical equations, V0 will cancel out. It's still useful because it tells us something about spatial transformations. If we change spatial coordinates within this homogeneous setting again, so we can't rescale them by constants, then we will also change V0. Or if we don't want to change coordinates, if there's curvature, then we might want to use a unit sphere just to have a specific value. We can still change the size of this finite region. So there's always a way to transform V0, and that's the only non-trivial spatial transformation that we have left in the theory. So it's useful to keep this parameter in there just to have some transformations that we can test, in particular after we quantize these equations. So we'll see this parameter V naught a few times in this first part of the talk. So as a brief summary of what we've seen so far, we have two important transformations. Time reparameterization, so whenever we see an n in our equations, we can see that's where we have to be careful with time transformations. And these spatial rescalings, which are indicated in our equations here by this parameter V0. And then depending on the specific spatial curvature, we may have spatial translations or rotations, which don't really tell us much because that's just about space and Euclidean or spherical or hyperbolic geometry, which we understand well. So after all this, the reduced action, so actually I didn't mention this, we have a longer expression initially from this general Ricci scalar for homogeneous models, but we can integrate by parts, and then some of these terms can be combined. So it's really just like a kinetic term and some curvature potential. So that's the action we have here. So even though we don't have the really interesting space-time transformations like local boosts, we have some time and some space transformations which allow us to test if covariance can still be maintained after quantization. Before I talk about this more, it's usually easier to do this in a Hamiltonian framework. So we use the Lagrangian. That's actually the action I'm still integrating here, so I should have called this S or removed the integration. Anyway, we know how to compute momenta, so that's the next equation here. There's no n dot after this integration by parts in the action, so n has a momentum Pn, which is constrained to be 0. We get a Hamiltonian, so the second term vanishes, and that's the expression. Because Pn is 0, that's called primary constraint, it has to be 0 at all times, which means Hamilton's equation with this Hamiltonian have to produce also 0, which implies a secondary constraint. And so this Poisson bracket is just dh over dn. It's linear in n, so it's easy to just remove n and take a derivative. And so that's our constraint, which if we insert the PA relationship here with a dot, is just the Friedmann equation. So we don't really get anything new, but it's presented in a new formulation. Here, there's a matter term. I didn't explicitly write down a matter action, but whatever matter we have, we can just start at the Hamiltonian here and add the energy. So this V0 times n, and the matter Hamiltonian would be added to this expression, and so we get the contribution also to the constraint of the Friedmann equation. So just reformulate it here. Now we can quantize canonically, so we use an A representation, wave functions depending on the scale factor, and then PA as a derivative operator. Usually we have to be careful here because we restrict A to be positive classically, so it's really a quantization on a half line. And this PA would not be self-adjoint in this case. But for our purposes here, we can ignore this problem. A simple way to go around it is to work with A, which can be positive or negative. And when it's negative, we just interpret that as space with the same corresponding volume, but the opposite orientation. So it would be left-handed instead of right-handed. So this interpretation is obtained naturally if we use a triad formulation instead of metrics. But again, I'm mainly interested in transformation, so we can ignore these more subtle Hilbert space questions. So there was a p-squared initially on the previous constraints, and now second order derivatives, and all these V0 factors are still there. And after transforming to momenta, they now appear sometimes in numerator, sometimes denominator, so we cannot just divide by V0 and eliminate it. It really appears in the equation. The solutions of the wave equation depend on V0, unlike the classical solutions. But first, a few more general statements. A specific example would be matter, which is just has a constant Hamiltonian, constant energy, so it should be dust. And if we just interpret this constant m as another canonical variable, as a momentum, canonically conjugate to some variable t that does not appear in the constraint or the wave equation, then Hamilton's equation will imply that t has to be constant. So it's consistent with the dust assumption. And as a canonical pair, we could then quantize these matter degrees of freedom, and we get just the right term. It's linear in pt, the matter part. We just get the right term to get something like a Schrödinger type equation. So we can, initially there was no time, it was just a constraint, not a full Hamiltonian. But this method can make it easier to interpret solutions as evolving wave functions. And to make it look even more familiar, we can use a canonical transformation of A and PA to Q and PQ. And then one can check that the kinetic term, which here looks non-standard, it depends on A and PA, but this canonical transformation brings it back to a standard, just PQ squared expression. So we can use just standard quantum mechanics intuition. So this procedure, or just as an example here, but in general, that's called deparameterization. So we use an actual canonical variable, which is initially one of the degrees of freedom, matter or from the gravity side. And we use it to formulate evolution equations. So that's called an internal time. And the first suggestion that I've seen was made early on by Dirac. Well, that's actually a classical paper, which I'm citing here. So I didn't quantize it at this point, but the idea was already there. So now with these preparations, I can describe the problems that can be addressed in these mini-superspace models and highlight those that I will actually be talking about in this presentation. So the first question here on this slide, or set of questions, is about time after quantization. And I'm assuming that deparameterization is used in some way. So there may be other ways to include time after quantization, but I'll be focusing on this deparameterization idea or generalizations. The first problem, even though there's time, it's not a time coordinate, and this n function has disappeared, which told us which kind of time coordinate we have. So that makes it more difficult to, even though there's time evolution, it's still difficult to interpret that. It's not clear how we would actually measure this t. So the physical meaning of t is not clear. Another question is whether this kind of internal time is always available globally. In this case with dust, that's okay because it's linear here. So we can just as we know that Schrödinger quantum mechanics always gives us unitary evolution for a silver-joint Hamiltonian, we can show that this just mathematically in this example, time, this big T here, will always be valid globally. But the problem is dust. The dust assumption cannot always be valid. clearly near the Big Bang, we should use radiation or something else, and that's a different equation of state, a different A dependence of the matter Hamiltonian. And so just for this reason, that this one specific example cannot be global. So we another option, which is very common, would be a free massless scalar, which is maybe more fundamental, certainly more relativistic. But it's also just one other choice. And this choice cannot be valid at late times because it would give us a stiff fluid. So energy density equal to pressure, which does not describe the later stages of cosmology. So we do have to transform between different times. And the question is, how can we do this after quantization in this deparameterization picture? Because for a specific time choice, an internal time, we get a fixed Hilbert space representation, and then we have to figure out how everything can be transformed to a new Hilbert space, or even within a fixed Hilbert space, can we, for instance, have a time variable that belongs to a dynamical scalar field, which would be oscillating, moving back and forth. And that's the question, this global question, which I'll be focusing on in the second part of the talk. The first part of the talk is about space. So here we'll talk about this V0 dependence. And from this equation, as already mentioned, it's clear that V0 affects solutions. So if we solve this wave equation, the solutions depend on V0. If we change V0, we get a different solution. And I'll go more specifically on the next few slides that also physical notions such as effective potentials depend on V0. So in classical physics, V0 always cancels out. In quantum physics, it's still there. It's supposed to be just a coordinate transformation. So we have to figure out if that's meaningful, if there's a good physical interpretation of V0 dependent predictions. The second question in this context, this V0 appeared because we used the minisuperspace truncation, just completely homogeneous space. And we have to figure out in which sense that can be good approximation to full quantum gravity. It turns out these two questions are related, so I'll be able to talk about both of them. So yeah, that was my introduction. And now I've already shown a few Hamiltonian equations. We've derived this Hamiltonian constraint. And also here, even if it's classical, V0 does not disappear as soon as we use momenta. And then this is our deparameterized Wheeler-DeWitt equation with dust. So that's from the matter term. Oh, there should be a D here. So that's the partial derivative of psi by big T. I've used this canonical transformation that I mentioned. So it's a standard kinetic term and some power law potential. So using standard intuition from quantum mechanics, V0 is a little bit like a mass parameter. It's 1 over V0 in the kinetic term, and then V0 times the potential. And we know from quantum mechanics that the energy levels, for instance, depend on the mass. So if we change V0, we should get measurable differences, if we can ever do quantum cosmology measurements, but its physical predictions will depend on V0. Just as an aside here, there's a negative sign. So it's not really a standard kinetic term because it's negative. That's related to another very fundamental issue of gravity. So it means that we don't really have a ground state. We don't have any distinguished state that would give us simple evolution. That's another question which one can analyze in many superspace models, but I won't have time for this in this talk here. So we'll turn to more details about this V0 issue. We'll actually use a scalar field model, which is easier to discuss, not gravity at this point. So the Lagrangian is standard scalar, kinetic, gradient, and some potential. And so that's a still field theory here, first line, so phi can be position dependent. So then we can test our mini superspace idea by reducing this to spatially independent phi and integrating. So also here we get the same B0 factor. And from now on, these phi's will be spatially constant. Canonical analysis again, so P is usually proportional to B0 because we take a derivative here. And just as before, the Hamiltonian now really depends on B0, not just as a simple factor, but 1 over B0 in kinetic term, B0 times the potential in the potential energy. And quantization here, just like minisuperspace using P and phi operators. Still a characteristic dependence, just like a mass in standard quantum mechanics. Now, in these next few slides, we'll derive an effective potential. So that will be a specific construction that tells us how predictions will depend on B0. To do this, we use a canonical derivation of effective potentials. Canonical effective theory, we use expectation values of basic operators Q and P. But that's not sufficient to completely describe a state in quantum mechanics. So we need additional variables which tell us what quantum fluctuations, covariances, and time moments we have. And a parameterization that describes all these variables is given by this delta of QAPB. So we take Q minus is expectation value, P minus is expectation value, so it will be the central moments. Some integer powers B, then whenever necessary, we use Weyl ordering or totally symmetric ordering, just to have real numbers and a specific ordering for given A and B. So these are infinitely many variables which describe a quantum state. One can show that that's actually a phase space or a Poisson manifold. So there's, you just have the definition here. Usually requires some calculations to actually get the brackets, but the definition of the Poisson bracket is based on the commutator. So if we have any two operators, then the commutator is antisymmetric, satisfies a Jacobi identity, and this will automatically be transferred to a Poisson bracket defined in this way for expectation values. Poisson brackets also have to satisfy a Leibniz rule or some kind of product rule if we multiply different expectation values. And this can just be included as an additional part of the definition. So with these constructions, we get a Poisson bracket which satisfies all the requirements. And this allows us to work with quantum mechanics just like classical physics. So we have a phase space, a Poisson bracket. And for the dynamics, we also need a Hamiltonian, which can also be derived from the quantum Hamiltonian as an expectation value. And then to express it in terms of these moment variables, we first rewrite it without changing anything. So just adding and subtracting Q's and P's. Then in the next step, we'll do something which is not completely well-defined, as often with effective descriptions. We assume that Q hat minus Q and P hat minus P are small in some sense. Of course, for operators, that's hard to make sense of in general, unless we have a specific class of states. But formally, if we have this assumption, we can use a Taylor expansion of the classical expression of H of Q and P and obtain something like this. So Q and P, now without hats, these are just expectation values. So that's the leading order, which appears from these Q and P background value. And then higher orders have two or more factors of Q hat and P hat, so that they give us moments. The term I wrote here specifically has Q fluctuations. Now there would be lots of higher order terms as well in general. With this definition, or two definitions, Poisson bracket and the Hamiltonian, one can check that the Schrödinger or Heisenberg evolution is expressed exactly in terms of Hamilton's equation. So if any operator O the time Drogodovic expectation value is equal to the Poisson bracket of the O and H expectation values.
So Martin, so this second term in the Taylor expansion, is that evaluated at Q equal to Q hat?
That's evaluated at Q equal to Q without a hat. So just the real number. Altogether the first term. Whenever there are no hats, they refer to just like classical values of Q and P.
Yeah.
So they would be, I didn't write the equation, but they would be just the basic expectation values.
Yeah, so you put it in the following equation you will get.
Right, yeah. And so Q and P, the expectation values have the same canonical bracket. So that's easy to see. If you have Q and P operators, then you get canonical brackets. Poisson brackets between moments are usually more complicated, and they're usually not constant, not always linear even. So they're not strictly canonical variables as like with momenta and so on. But it's possible to construct position and momentum variables even for the moments, just as a consequence of the W theorem. So whenever we have something symplectic, then one can use, well, it's an existent theorem, so it might still be complicated to get these canonical variables, but they exist. So in principle, one can always rewrite these as other pairs of variables, which is actually very useful in derivations of effective potentials. But for what I'm doing here, we won't need this.
Yeah, sure.
So to get the effective potential, so that's now applied to our scalar mini-superspace Hamiltonian. So classically, it was just the first two terms without the brackets and hats. So now we have momentum and phi dependence. The momentum dependence is always quadratic, so the only corrections we have there is a second order moment. One can also see this directed without Taylor expansion because the square of the expectation value plus the variance is equal to the expectation value of p hat squared, which is exactly what we get in this expectation value. But then if the scalar potential is not quadratic, we do have an expansion here. So I will use only the first correction. So second order derivative of the potential and the variance of the scalar. So, and then I stop. So it will be a semi-classical approximation. First order H bar. And I didn't work out all the Poisson brackets of the moments, but this can be done. So using this Hamiltonian here as an effective Hamiltonian, we can generate Hamilton's equations of motion. And this tells us that the fluctuation and the covariance of phi and p evolve according to these coupled but linear differential equations. Well, linear in the moments, and then there's non-linear in phi. So, well, for generic potential, we cannot solve this equation, but for kind of low energy effective potential, we're interested in solutions which are in some sense close to the ground state of the system. The ground state is stationary, so we can use an adiabatic approximation, which means to leading order, we just set all the delta dots equal to 0. And this directly tells us that the covariance has to be 0, and there's a relationship between delta p squared and delta phi squared. It doesn't fix each of these individually, but if we also saturate uncertainty relations with the equations we already got, we got specific expressions for delta phi squared and delta p squared. Well, this looks like an extra assumption. In general, if it's an interacting scalar, it's not clear why the ground state should saturate uncertainty relations, but independently, we can also derive this condition by minimizing the effective Hamiltonian, which we should do for the ground state. So that's like the variational principle. Because the effective Hamiltonian here is linear in the moments, it doesn't have a local minimum. But the moments are restricted by uncertainty relation. So they take values in the bounded space, and minimizing this Hamiltonian just sends us to the boundary. The boundary of the uncertainty relation is saturation. So this more general minimization condition also gives us the same values. So now we have delta phi squared delta p squared in this approximation. We can insert them back up here in our effective Hamiltonian. Set the p expectation value equal to 0 because we just want to extract the potential. That doesn't mean p always has to be 0 in this approximation, but just to see the potential, we should eliminate the kinetic terms. And then all the remaining terms can be combined to this expression, so a classical potential and then an h-bar correction. Also written explicitly here. And we see it depends on V0. So it's not just wave functions, which are not directly measurable. So we have wave functions depending on V0. One could say maybe it disappears and when we derive actually measurable quantities. But the low energy effective potential derived here is not subject to any of these questions about the wave function, and it clearly depends on V0. So even though the classical equations are completely invariant on the rescaling V0, the quantum equations are not. And if we don't really know what V0 should be, the value, classically, we don't know anything about it. If we can choose any arbitrary value, we could make quantum corrections large or small, whatever we want. It's just not predictive. Just a brief remark about an alternative derivation. So even if we don't use canonical derivations, you can see the same scaling behavior using a path integral. So the Hamiltonian, I should show this. When we derive the Hamiltonian, it depends on, it scales like V0. So P scales like V0. So P squared over V0 also scales like V0. So if we rescale V0, P and the Hamiltonian scale in the same way. So H, the exponent here depends on V0. The measure depends on V0 through P. But it always appears in the combination V0 over H bar. And that's also the combination that we have here. So it's a very general scaling behavior. It doesn't depend on the specific model or derivation. So what do we do about this V0? Now it turns out it's, in this case, it is actually very useful to try and go beyond these minisuperspace models. And for scalar field theory, we know what that is. In terms of low energy potentials, it's the Coleman-Weinberg potential. And I should thank Hermann here for, several years ago, he suggested that we should look at the Coleman-Weinberg potential with these canonical methods. And we did, and that's how we noticed this relationship with minisuperspace truncations. So the original result is written here without the I that we would have in Euclidean space. So I changed this to Lorentzian space-time signature. And briefly after Hermann's suggestion with Ashuto Brahma, we were able to rederive this potential just based on moments. So like an extended version of the calculation on the previous slide. It looks like this, not quite the same, but then we noticed if one can actually do the K0 integration, time component of K. One can do that explicitly. And if you do this, you get the second line. So it is really the same expression. Now the second line here looks much more like our square root of W double prime, which we got from our minisuperspace. In fact, if K is equal to 0, it's exactly of the same form. Or if K is not completely 0, but small, so in the infrared regime, long wavelength, small wave number, then we can do here, also here, a Taylor expansion of the square root and derive our effective potential with a slightly different numerical coefficient. But the important point here for our discussion is if we relate the infrared contribution to our V0. So we have this V0, which tells us what region we have in which we want to use homogeneous models. Then if we include everything that has wavelength larger than the radius of this region, then we are only including those modes that are actually contained in our minisuperspace description. And these modes are well described by the minisuperspace potential. So if there's structure only beyond the averaging region, then the effective potential is a good description in the minisuperspace model. If there's significant structure on scales smaller than V0, or if ultraviolet physics is important, then the minisuperspace model is not a good approximation anymore. So in this case, we do have a more controlled minisuperspace approximation. And we can see that we cannot actually choose the V0 value here arbitrarily, because it's related to the relevant scale of structure inhomogeneity in the setting. If we try to make V0 very large, to make quantum corrections smaller, then we're eliminating more and more modes from this approximation, and our approximation gets worse. In quantum cosmology, in particular loop quantum cosmology, people initially actually suggested that one should use large V0, and then correct can be completely ignored. But this was based just on the numerical value. So that was before the relationship with inhomogeneity was recognized. And then the same large value of V0 was used even at the Big Bang, or bounds in this case, where we should clearly not assume large-scale homogeneity. So these considerations do tell us something. They really help us to interpret the validity of minisuperspace models. So I think that's a summary here. So we now have an interpretation of V0. We know that the dependence of physical predictions on V0 is meaningful after quantization, even though classically they don't depend on V0. That's because if it's quantized, we have interactions between the modes, and depending on which ones are relevant, we have to use a specific range of V0. So with this relationship between V0 and the infrared scale, this dependence becomes meaningful. So the size of quantum corrections depends on V0, but then the choice of V0 is related to the maximum K, or which kind of infrared contribution we should use. So we have to know more about the structure of inhomogeneity. So a single minisuperspace description is not sufficient because it doesn't tell us anything about where V0 should be. So we have to go at least a little bit beyond minisuperspace truncations to be able to derive a good value of V0 at any given time during cosmic evolution. So if we don't have this relation, we might be tempted to choose large V0, but then the approximation gets less accurate. So the good news is minisuperspace models do tell us something about the full theory. We have to be very careful, but there's something. The derivation here suggests an improved version, actually as an approximation, not just a truncation. Go back to this expression. Here, I really just used the first order expression and the Taylor expansion, but we can be more careful and expand the square root. So we would get higher order terms, and depending on how close we are to where inhomogeneity becomes important, these additional terms, higher order terms and Taylor expansion of the square root, can improve the approximation. But to do this, we have to know the square root, or some analog of the square root in a quantum gravity theory. So we really have to we need more information about the full theory before such an expansion can be done. Another question, again, I won't be able to talk much about covariance or space-time transformations, but we now know that any mini-superspace construction depends on V0, and V0 is related to the infrared scale. So if we apply a transformation, the wave number is not invariant. It might change. And what we have here, of course, is only the spatial norm, not the space-time norm. So if we try to embed this in a covariant theory, which we haven't really done yet, there's an important question here about how the infrared scale will be related to covariance. Something else which we haven't fully done yet is infrared renormalization. So in cosmic evolution, if we maybe consider a collapsing universe, we evolve towards a Big Bang, then inhomogeneity usually builds up. And this means that we have to adjust V0. We can use a large V0 at late times, where we have large-scale homogeneity, and then quantum corrections will be small. But as we approach the Big Bang, and a good picture here is BKL, inhomogeneity usually builds up. BKL tells us we can still use homogeneous dynamics, but it doesn't give us any lower bound on the size of regions in which homogeneity can be used. So, but generically, we expect that inhomogeneity builds up. So we have to reduce V0, will become smaller and smaller. And that corresponds to infrared renormalization. So also here, we have to go beyond mini-superspace models, because in addition to mini-superspace evolution, we will have to derive how quickly inhomogeneity builds up and then adjust V0 in the mini-superspace model. It's more complicated than standard quantum cosmology, because any fixed Hilbert space in usual treatments has a fixed V0. V0 appears in the canonical structure. And so the Hilbert space will also have to be changed. And then eventually, since BKL doesn't give us any lower bound on the size of the regions, eventually this infrared scale will be pushed all the way into the ultraviolet. And then by that time, at the latest, mini-superspace approximations break down, because that can only be described by the full quantum theory. So last two are still open questions, but as I promised, we have learned something about spatial structure even in these mini-superspace models. So that's about the first half. The next half will be about time. So if there are any questions about this V0 or canonical descriptions, I can stop here and take those questions.
Guys, please ask questions.
Hi, Martin. It's Aureliano.
Hey.
I didn't quite follow your statement there that we cannot use a fixed Hilbert space. Can you go around that again, please?
Yeah, that your son in the background.
Yeah, sorry.
No, that's good. Yeah, well, yeah, I didn't show an actual Hilbert space construction. Let me see, but when we derived, yeah, momenta. So the yeah, let's say the Hamiltonian. So the so if you have a fixed, let's say a Hilbert space representation, so you represent phi and p and h in this example, and then you have to put V0 into your h, and quantum equations will only tell you how phi and p change, but there's no operator for V0. It doesn't have a momentum. So the only way to change or to adjust V0 is by just modifying it by hand, just switch to a different value. Now, this would be a different Hilbert space representation. So yeah, you might be able to use the same kind of wave functions, but the actual operators that you're representing on that Hilbert space would have to be transformed by hand. And this can be done. There's no basic problem that would prevent us from doing this, but we so if you try to do numerical quantum cosmology, you will have to evolve your wave functions, but at the same time you would have to evolve inhomogeneity, so use some kind of numerical relativity code and extract V0 and put this back into your Hilbert space representation, and then start over and evolve with a new V0. And yeah, then I'm actually not sure about this step, because then what happens with unitarity here? So you're suddenly changing your Hamiltonian. I guess it could still be unitary, you have a finite time transition amplitude up to where you're adjusting V0, and then change V0 suddenly and just follow up with a new finite time evolution operator. So I guess it would still be unitary, but you still have these sudden changes of V0, which could have some implications on the wave function. We haven't tried it yet, so I'm not really sure what happens.
Got it. Thank you.
I can ask a question, please.
Please ask.
From what I understand in cosmological perturbation, we use sometimes these, we do some gauge fixing kind of thing. We use the new kind of Sasaki variables and the Bardi potential. And I mean, I haven't tried it yet, but doesn't this make the Hamiltonian independent of V0? I mean,
I don't think so. Not if you, yeah.
What's the use of fixing the gauge? Isn't to make this Hamiltonian generally covariant? I mean, that's how I understood, at least.
Right, but then in addition to making it covariant, so it will be invariant under linear coordinate changes.
True.
But then, so you can do this without choosing any finite size region. But then, if you try to rework Mukhanov-Sasaki variables canonically, then with a background plus perturbations, you would have to introduce this V0 for your background variables. And then the momenta will depend on V0, and the Hamiltonian in terms of canonical variables will depend on P0 or on V0.
Mm-hmm.
So that's a very general relationship which cannot be avoided. Just the way the background dynamics works canonically.
Mm-hmm.
And even, I mean, my arguments here refer to canonical quantizations, but just as in the brief statement, where did I have this, about path integrals, you have the same V0 factors appearing in the measure and in the exponent as soon as you use the canonical path integral. So, which should of course be equivalent to the non-canonical version, but it's easier to see the factors in this canonical picture.
I see. Okay, thank you.
More question, please. Don't write. Please ask. Oh. Oh.
Yeah, I won't be able to see any written comments.
No, sorry, I have to go to a meeting. So I'm sorry. I was asking if the rest of the talk is going to be online.
Yeah, this talk I will post in YouTube. You may check from there.
Yeah, it should be there. It's also, the second half is based on a very recent paper from this year about periodic time. So with a few new results which aren't published yet, but that's the main topic. Okay, if there are no more questions.
What about my students? Abhinash Shattoki, please ask question.
Not right now. Like they're trying to process things, so fine. Thanks.
What about Shattoki? I can't able to hear anything. Okay, then Martin, you proceed.
Okay, good. It's about halftime now, right?
Yeah, but yeah, it's a really nice explanation. So you gave me this paper to read. Remember?
Yeah, yeah. Some of the canonical ones, right?
Yeah, the previous one you gave me, and the application in quantum chemistry.
Right. Yeah, I didn't mention that actually. I wanted to mention this. So the this kind of, not the low energy potential, but this kind of moment expansion has independently appeared several times actually. People has used it in quantum chaos as well, in quantum chemistry for some time.
Yeah.
And they've extended it to higher orders as well. And we've recently taken up this direction. So, and they also, these taboo variables, yeah.
How they interpret this V naught in those systems?
Well, they don't have V naught because they're classical. It's just the standard classical mechanics H,
Okay.
which does not have a V naught, but they have the same kind of. And for these second order moments, they worked out the Dabu formulation. So there's a pretty simple way to write delta phi squared and delta p squared in as configuration variables and momenta.
Sure.
The if I remember, yeah. So the so delta phi, well, the square root of delta phi squared, or just the phi fluctuation, would be a configuration variable. And then I think it's delta phi p divided by the square root of delta phi squared is the momentum. And then delta p squared is
or something like that. Yeah.
Yeah. Yeah. If anyone is interested, send me an email. I can send you a reference to the quantum chemistry review.
Yeah. Okay, you can proceed.
Okay. So yeah.
I remember that you gave me when you saw that I gave the talk on this chaos stuffs. Yeah.
Right. Yeah.
Okay, you can proceed and like. Thank you.
Yeah. So the second half will be over time. The methods will be quite different. So in this case, we haven't really figured out yet how to use a good effective description. So we'll be based more on wave functions. And conceptually, there's a basic question. So physically, maybe it's more interesting. It's really about time now, which is much more mysterious than space. And we have two different ideas about time, which are often contradictory. So what we experience directly is a monotonic flow. And it's directed, I won't talk much about the era of time here. But the way we actually measure time is by periodic processes. So we'll refer to this as time and clock, and this will not be the same in my discussion. Now, there are many reasons why we use periodic processes to measure time, because it's easier to keep track of change by counting cycles instead of following gradual change, in particular in terms of precise measurements. So there are practical reasons why we use periodic processes for clocks. So that means it doesn't necessarily imply that time fundamentally has to be periodic. But there are other fundamental reasons which make this more likely. And I'll talk about this a little bit in the next few slides. But first, fundamentally, there's also a contradiction here, because relativity and quantum mechanics tell us something different about time. So the first case, relativity, we know that time can be transformed, and if there's curved space-time, then we usually have to we can use a specific choice of time only in a finite region. So this looks more like a periodic picture. Or at least, even if time doesn't move back, it's kind of put together in small pieces. Quantum mechanics, the way we really formulate it, requires unitarity. And so there's a single evolution operator valid for all t. So that looks more like monotonic. And there's no time operator, which also indicates that the time in this formulation is not really fully treated as a fundamental object. Now back to Dirac's old paper with a more detailed quotation here. So that's the sentence in which he suggested deparameterization. He didn't call it that, but it's like the suggestion. So he suggests that time should just be like one of the configuration variables. So this would be t here would be time in my language, and q0 would be a clock degree of freedom. So conceptually they're not the same initially, but then he directly relates them by imposing this differential equation. And this, the second condition here imposes monotonicity of time, or the clock here, because if q0 dot, the derivative by t is equal to 1, then q0 has to be monotonic. But his motivation was different, so he uses it's mainly as a simplifying assumption, but fundamentally this condition would have to be justified if we would need a good reason to say that time should be monotonic if we wanted the equation strictly. Also here the canonical formulation helps. So it shows that this second condition is not actually something we can choose. It follows from a more detailed formulation of the first condition. So to this canonically, we use our standard canonical pair x and p. And then time phi, so I follow cosmological notations of q0, like Dirac, I call it phi. It also has a momentum, and relativity tells us that because space and time are part of a four-vector, energy and momentum are part of a four-vector, the momentum of phi should be related to the energy. And then there's a minus sign here, which comes from the Minkowski metric. So we have an extra canonical pair, but we don't have an extra degree of freedom. There's still just one independent variable, which should be time. And that's included here in this formulation by an additional constraint. And that's also not free to choose. It follows from the fact that the energy is always equal to the Hamiltonian. The energy is now a momentum of time. The Hamiltonian depends on xp and phi on other variables. So this equation is actually a constraint equation on this extended phase space. And because there's a constraint, there's really just one independent variable. So it's correct from this general perspective. And then if we use Hamilton's equation for this constraint, we learn that d phi over dt has to be equal to 1. Because phi is canonically conjugate to minus e, so that's what it is based on Hamilton's equation. And that's Dirac's condition. So he wasn't really making this choice freely. It wasn't a choice at all. It follows from his own constraint formalism, which he hadn't really developed at this time. But the second condition follows, which means it looks like time really has to be monotonic because there's this condition which we just derived. But the derivation used additional assumptions. For instance, in way of writing this constraint, we just used the linear relationship. But one could have other equations that impose E equal to H, and that would modify the equation down here. So in cosmology, then back to the Friedmann equation here without this n function, because I'm mainly interested in internal time, and without B0, because we've already talked about this. So the canonical pair here, if we just use a cubed as a variable, the momentum is proportional to the Hubble parameter. And we also use a scalar field with momentum p phi for a matter Hamiltonian. So we're first the density here, and then just a massive scalar would give us this expression. So this constraint is different from this classical type, classical mechanics equation. This one is linear in E, or which would now be p phi. This equation is quadratic in p phi. So to compare these, we can factorize this constraint first. So we get some Hamiltonian here. It's a more complicated square root expression. And then C is equal to 0 if either of the two factors is equal to 0. So we get the previous equation or the opposite sign. But the Hamilton's equations are now different if we use the full C, because not just a constant anymore. We take a derivative by p phi. So depending on the formulation, in particular, it's relativistic, the dynamics of the time variable may be more complicated. Now, what's usually referred to as deparameterization in a strict sense is a global notion of internal time. And in this example, that would correspond to 0 mass. So in this case, then the square root is easy, and we get a simple Hamiltonian, which is phi independent, time independent dynamics. So a lot of things simplify, and p phi doesn't change. So we can always work with just one of these two factors. So in this case, we know how to quantize this dynamic. So that's like the dust example, where we have a global time unitary evolution. But for the scalar field, that's, yeah.
Martin? So because of the square root, there is a problem of quantizing?
Yeah, there is.
Yeah.
Because we, and clearly, if it's quantized, it would have to be valid for any phi and PV, where it can easily be, the combination can be negative. So this Hamiltonian would not necessarily be Salvatron. And you could do something like an absolute value around the difference here. But even if you have a Salvatron Hamiltonian, it's time dependent. So dynamics is still more complicated. I'll talk about this in more detail, but if you look at the factorization here, if you try this for an operator, it works like this only if H commutes with P phi.
Yes.
But if M is non-zero, they don't commute.
True.
So that's one of the difficulties. There are actually several different ones. So making sense of the square root as an operator, which can be done. So you can if you can compute the spectrum of what's in the square root, you can just take the square root of the absolute values of the eigenvalues, and that defines the square root of an operator, but it's more complicated. And then there's the question about the commutator. So usually in quantum cosmology, that's the case that's used m equal to 0, just because it simplifies things. But it's not realistic if it's fundamental, because we would need the scalar field just for the purpose of playing the role of time without interacting with anything except gravity through its energy. It would not have mass, it would not have self-interaction. So it looks like a very special situation. Not really fundamental if it's not really interacting with anything. So the question is if one can make this more realistic by making sense of time and evolution for non-zero mass. And I'll talk about this a little bit here. First, clocks have been used in cosmology in a different context. So just to avoid confusion, I mentioned here that our clocks, fundamental clocks, are not the same as what I call spectator clocks here. So the previous cosmological application was also massive fields, but not quantized, and they were used to detect possible changes in the scale factor dynamics in the early universe. So what we have here in our fundamental clocks is also massive, but it may be much more massive. It might be Planckian, it's fully fundamental. And the way we deal with our fundamental clock as a constraint implies certain differences, in particular after quantization. And the main effect we'll see here will be in coherence properties of wave functions. So it's really fully quantum effect. So now I'll do quantization more slowly because it's subtle. So we introduce operators for all these canonical variables. A basic commutator is also here with the minus sign for this phi e pair. And we have a quantum constraint. So same combination minus e plus h, but now acting on y functions. Also here we see that time is still monotonic or no different from standard treatments because this basic commutator here implies that E is IH or D over D phi. So the constraint equation is completely equivalent to the Schrödinger equation. So it doesn't change anything, even though we initially introduced a time operator, it's basically eliminated by imposing the constraint. So it's still in this monotonic time situation. And also we haven't really put x and phi, space and time, on a completely equal footing because the constraint is treats E and x different, so E and P differently. So it's always linear in E by construction in this case, but usually quadratic in H. So in principle, we could try to solve this for P instead of E, and we would get a more complicated wave equation, but we don't do that because the dependent on P is more complicated. What we can also see here is because we know there's no time operator in Schrödinger quantum mechanics. And one can show in more detail that that's actually an implication of imposing a constraint. So it eliminates, if we solve it for phi, or the phi derivative, the same procedure eliminates phi fluctuation. So that's imposed by the constraint. But the first property is something that we can change. We can try to work with more general constraints, as in cosmology, which depend on E or P phi quadratically. So I call this a relativistic energy equation. And for these examples, simpler than cosmology, I'll model this on the standard mass equation. So, and then I replace P or P squared plus M squared with the square of some Hamiltonian. Now that's quadratic in E. Still different in P because if we square P, it's now quartic in P. So we are still kind of dealing with the same kind of unequal behavior, but with a more general constraint, which is not restricted to be linear in E. So now Hamilton's equations for phi and E are more complicated. So d phi over dt is no longer constant necessarily, unless E is constant. And E is constant if H is phi independent. So if we have a phi independent Hamiltonian, then we are still pretty much in the situation of Dirac, where he had a constant d phi over dt. E could be positive or negative, so time might run forward or backward, but it never changes between forward and backward motion if H is phi independent. If H is phi dependent, this would be like the massive case in cosmology. It's very different because E is no longer constant. D phi over dt is no longer constant, and phi might oscillate, E might oscillate, so it might really connect forward and backward motion. So in this sense, relativity prefers periodic clocks. So as soon as we make the dependence on E quadratic motivated by relativity, we get this, or generically at least for phi dependent H, we get this oscillation between forward and backward motion. But then we have this question about operators. Also here first the time independent case. Well, that's where we know what to do if in this case E and H commute. So we can exactly factorize this quadratic expression in two ways. The two factors commute, so it doesn't matter which one we use. Any one of them can directly act on the wave function. So we still get Schrödinger quantum mechanics in two versions actually, because E could be plus or minus H. And that's what we need for a periodic clock. We have to move up and down, and that's the two sign choices. And both of them can be implemented on the same Hilbert space here, because the factors commute. If we have a time-dependent Hamiltonian, it's very different. We can still try to factorize, but there's an extra commutator term, which is no longer zero, to relate to a derivative of h by phi. This could be a quantum correction, it's h bar, so if that's the only term, that's okay. But the problem is the two different orderings here give us the opposite signs. So we cannot use a single constraint or a single Hilbert space implementation of this constraint for both forward and backward motion. Given only half a clock, not a full clock cycle. And in this sense, quantum mechanics seems to dislike periodic clocks. So one question, even before we introduce gravity, a question about relating relativity with quantum mechanics is, how do we make sense of periodic clocks in quantum mechanics? And I'll show you how this can be done on the next few slides, but first a different viewpoint. One can also analyze this from the perspective of gauge theory. So if we choose phi as time, then we impose a condition phi equal to t with the real parameter, an external parameter, no longer phase-space coordinate. And that's a new equation, an additional constraint, and it does not Poisson commute with our C prime unless E is equal to 0. So it's a gauge fixing condition. It turns the single constraint into a second class pair. So if we choose a specific t, just put it on a specific time slice, we fix the gauge. We should cross our gauge orbits. If H is phi independent, so also here this distinction, E and C prime Poisson commute, E is constant. So as long as we choose a non-zero initial value, it will always be non-zero. And we will always have a good gauge fixing condition here. So if the Poisson bracket is non-zero, we have a real slice transversal to our gauge orbits. If H depends on phi, E is not constant. And if we have an oscillating phi, E will also go through 0. When it does so, the Poisson bracket is 0, and gauge fixing surfaces are no longer transversal to gauge orbits. So the gauge breaks down. We have a Gribov horizon in this language. And also just a little bit of quantization. Quantization, mainly in terms of path integrals of gauge theories, tells us that we should never cross a Gribov horizon in the path that we sum up. Because if we do so, we overcount degrees of freedom. Because beyond the Gribov horizon, the gauge fixing doesn't properly distinguish between different gauge orbits. So if we implement this here, we should never cross Gribov horizons, which means we should always work with a fixed sign in quantum mechanics and path integrals in this case. But then we're back to the question, how can phi oscillate if d phi over dt is 2e and we have to fix the sign of e in path integrals? So again, quantum mechanics, again, previously canonical with these commutators or path integral give us the same answer. It doesn't seem to like periodic clocks. Now, what we noticed in this paper with Marcelo Amaral 3 years ago is that one can actually generalize these conditions, and it is possible to make sense of periodic clocks. Instead of using d phi over dt equal to 1, which in some way presupposes the direction of phi, even if it's derived from this linear constraint. But this linear constraint can be written with two sign choices. So it could be a plus minus here, and then the plus minus choices would give us a plus minus in d phi over dt. So phi could run back, forward or backwards. So more generally, we should try to have a relationship between phi and now what I call tau for global time, which takes into account the sign choice. So at some cycles, it might be plus tau plus a constant, and others it might be minus tau plus a constant. with constants are chosen for continuity. And if tau is time, the time we actually measure experience should be monotonic. But phi could oscillate if we just repeat plus and minus tau cycles. So this parameterization would be more like a periodic clock, phi, which rolls on a linear scale and in this way imprints a monotonic time label, or time and date. What we usually call time in a strict sense is still periodic, but as soon as we go to at least the year, it becomes non-periodic. So we have to implement this parameterization. Now, one indication that this also might solve the dynamical problems is if we now still use the standard Schrödinger equation, but write it for tau, a tau derivative of psi, the chain rule gives us an extra factor. So the psi or d phi follows from the constraint with E here, but we get an extra factor d phi over d tau, which can be plus or minus 1. So even if we just have a single factor like this, not the two factors that we had in the time-independent treatment, we can still get a plus minus h, because d phi over d tau can be equal to plus or minus 1. So in this way, we can just have a single factor. We don't have to solve this factorization problem, even if h is phi dependent, and still have forward and backward motion with respect to global time, tau. To show how this works, here's a more specific example, still a generic h, but I pull out a phi piece out of h here. H depends only on x and p, and I assume a phi potential in addition to E squared. And then there's a coefficient lambda, which would be like a mass term in cosmology. So now we have an oscillating clock system. It's a harmonic oscillator, Hamiltonian. And X, some other system. There are no link to X times V or something like this, but the constraint itself, it's an energy balance condition instead of a force, implies that the dynamics are related. Now in this specific case, because there are no coupling terms, Hamilton's equations imply that H is constant. And for any constant H0, the constraint implies that E and phi move on an ellipse, as shown here. I will be interested in a case of very short clock periods, so large clock frequency lambda, which means the turning points are very close to the origins. It's really very short extension in the phi direction. And the clock system runs through these cycles very quickly, much faster than the system. So this should make it possible to actually resolve time in a precise way. I put frequency here in quotation marks for lambda because it doesn't have units of a frequency. It has units of energy over time, but it still tells us how quickly the clock goes through its cycles. Now with this system, just solving C equal to 0 for E implies this expression similar to our square root in cosmology. We can choose the sign of E, so just to be specific, it's positive. And then as a Schrödinger equation, at this time just for phi, we get this equation. I'll use an energy representation for wave functions, so eigenstates of H, which means these are just constants on the right, assuming we know the eigenvalues. And the square is still kind of complicated, but this equation can be solved. So that's the phase. And it's nonlinear in phi, so it replaces the usual linear phase for time evolution. Also here, if that's it doesn't work because it's not unitary. The phase, the square root, and the arc sign are real only if phi is between its two turning points, ek over lambda, previously h0. And so phi evolution would not be unitary because once we hit a turning point, it's the phase is imaginary or complex. Now this can be solved with this tau evolution. So here, some maybe complicated equation, but we have a plus tau and a minus tau version, and constants for fixed lambda and dk, which impose continuity. So it's really just this zigzag line here with plus minus 45-degree slopes. So as tau changes monotonically, phi oscillates up or down. There's a new parameter n here, which is the number of clock cycles starting with 0 at tau equal to 0. And so at some large value of tau, we can in principle determine how many cycles the clock has gone through. So now for tau evolution, we have this extra factor of d phi over d tau. So this means the phase is multiplied with this factor when we solve this equation. So whenever we change from upwards to downwards motion here, we have to change or invert the sign of the phase in addition to just doing standard Schrödinger evolution. So it's a slightly different process. But with this change, or using phi of tau, we have unitary evolution because phi of tau, as one can see here, is always between the turning points. So this square root here is always real, and we always have unitary evolution. That's for a single eigenstate, and then we have to use superpositions of some psi k, some coefficients, depending on initial values, the initial state. And this would give us full evolution. So each state, each eigenstate contribution would go through its turning points at different times because the turning points depend on the energy of the system. So as we start going through turning points, different eigenstates get out of phase. So we expect that coherence quickly breaks down. At that point, it was hard to tell what exactly happens just based on analytical calculation. So more recently, with at that time an undergrad student, Garrett Wendell, and a graduate student, Luis Martinez, we worked out a numerical solution, and we can here. That's actually an even more specific system. So the system Hamiltonian is quadratic in the potential, so also just a harmonic oscillator. So what we expect for 0 lambda is, in this case, it would be standard quantum mechanics of a harmonic oscillator. So an initial Gaussian state, which is what we choose here, should remain coherent. But for non-zero lambda, when these turning points kick in, different eigenstates lose their phase relationships to the others, and coherence is quickly lost, what we can see here. So that's a density plot, and this on the left, the smaller one, plots the Q and P expectation values on the plane, and then time runs up vertically. And the colors indicate the quantum fluctuations. So as also here one can see quickly, coherence is lost, and the expectation values just move around almost randomly. We can see it's related to turning points. Lambda is 10 to the -1, so the first turning point should appear at about tau equal to 10. And that's exactly where coherence quickly gets lost. So at this point, initially we thought it just doesn't work, because if coherence gets lost so quickly, we do observe coherence in specially prepared quantum experiments. So that would be a huge contradiction with observations. And if it's really a fundamental clock, it might be a Planck time period. And so after one Planck time, we would already lose coherence. So the surprise was that it actually behaves much more well defined. This is a plot which initially would say it's lambda equal to 0. That's a completely coherent state, dynamical coherent state, so it keeps its coherence. But it's actually a huge value of lambda, 10 to the 10. So there are billions of turning points even before we get to the first minimum. And there's no visible loss of coherence in this picture. So these turning points, somehow, if they happen rapidly enough, they reinstall coherence. So this shows that periodic internal times are actually meaningful. So we do get unitary evolution, which was shown by these analytical considerations. And it is consistent with long-term coherence in systems that should be coherent, like the harmonic oscillator. There are a few additional details which are useful for potential observations. One difference here is if we look at the period, so it doesn't start at 0, but the first period is finished about here, which is close to 2 pi. That's the correct period for this kind of Hamiltonian, omega equal to 1. If we look at this here, the first period is finished at a value closer to 8. So there's a difference, not in coherence, but in the period. And this can be derived, so that's the first check that the analytical calculations also work. So that's a calculation in the large lambda limit where we can use certain approximations. So we can first compute the number of clock cycles. So we had this expression earlier. For large lambda, we can ignore the +1. So it's a simple expression. And instead of following this complicated nonlinear phase theta k, we can just add up small phase changes in each clock cycle. So for a given number of clock cycles, we go through this 2n times 2 because these are the phase difference give us half cycle contributions, and then after a half cycle, we change the sign of the phase. And as phi moves up, we add the same amount. So the phase changes between the turning points times 2n is the total accumulated phase. Also, this simplifies considerably compared with the square root and arcsine expression of theta k, just by evaluating it at the turning points. So the final expression is, again, linear in tau, just like the standard quantum mechanics phase. But it's multiplied not just by energy over h bar, it has an extra factor of pi over 4. And this factor transforms a frequency of 2 pi into a frequency of 8. Or sorry, a period of 2 pi into a period of 8. That's observed here in these plots. That's a difference which we can explain, but it's not observable because the pi over 4 factor is the same for all energies, for all systems. So we can just include it in our definition of a bare frequency of whatever system we consider, and then it will disappear. So that's not observable. But the next order terms in lambda are observable. There's a variance here, which we can compute. So we take the nonlinear phase, subtract the linear accumulated phase, square it, and average it over a quarter cycle from 0 to phi t, because after that it will just repeat itself. That's an integral which can be done analytically with this value. Ek and lambda still refers to individual eigenstates, but we can replace all these with the clock and the system period. The clock period is 4 times the turning point value, so 4 Ek over lambda. The system period as usually is 2 pi h bar over Ek for a given eigenstate. So if we use this, then the relationship here only depends on the 2 periods and the variance, which is a new implication of this periodic clock treatment. And the numerical factor evaluates about 10. So that's a new dephasing effect. So it comes from this nonlinear phase combined with sign changes at the turning points. It's very generic. It requires only nonlinearity and turning points. So for any generic phi-dependent Hamiltonian, that's what happens. The numerical factor might be different for other clock systems, but there should always be such a relationship. Now this is just a quarter clock cycle. It doesn't tell us anything about long-term evolution, but numerically, one can go back to this wave function for large lambda and extract the periods at different times, or it's some kind of statistical ensemble for which one can compute the variance and compare with our analytical derivation. And it's very close. It just gets more difficult to resolve the periods as lambda gets larger. So even for actual long-term evolution, we can still use the variance. And that has an observable implication. So if we have a system which can be measured very precisely, accuracy sigma, then the clock period is bounded from above, because if it were larger than about 10 sigma TS, we should not be able to measure TS so precisely, because these dephasing effects would mean that even an electromagnetic wave that's used in an atomic clock would not have a constant period. And so there would be a new fundamental inaccuracy. Now we do know that system periods can be measured pretty precisely. The best examples are the latest atomic clocks, sigma about 10 to the negative 19. The system period here is not very large. That's femtoseconds for visible light. But the extra factor of sigma brings it down by many orders of magnitude. So the upper bound we get for the clock period is about 10 to the 11 Planck times. Still far from the Planck scale. But if we compare this with direct measurements, so particle accelerators probe about 10 to the negative 20 meters, that's 16 orders of magnitude above the Planck scale. Or as a time resolution using the speed of light, it would be 10 to the negative 28 seconds. And here we have an indirect bound of 10 to the negative 33 seconds. So this new effect actually is useful. It's not, there's no direct observation related to it, but it gives us new and sharper upper bounds on the possible clock periods. Here are examples for anharmonic systems. The clock can also be anharmonic, and one can see similar effects. That's a hydrogen example. So small lambda lead to additional variations. Large lambda give us much sharper, in this case, expectation value trajectories. Now, what about cosmology? So that's where we are still working on it. So that's work in progress. It's more complicated. So maybe the motivation here is like before. So we have the scalar field, but then in cosmology, we have additional volume factors. Not just the B-zeros, but really as a phase-space coordinate. So the clock and the system contributions are not as separated as in the previous example. So there's an actual direct interaction between V and phi. Now this has implications. The dynamics is more complicated. Equations of motion derived from this constraint have Hubble friction. So if V dot over V, which is the friction coefficient dynamically, which I'll just refer to, well, that's large, so I will refer to this as small v, then the potential here is reduced, the clock potential. So phi doesn't really oscillate very much. So if we have large Hubble friction, Planck density perhaps, phi is actually, for a pretty long time, it's a good monotonic clock. So in this case, one can use deparameterization. But as V increases, we extend the Planck regime to an expanding universe, then the potential increases, so turning points of phi appear, and just a few at first. So we are in the small lambda situation in the harmonic example, and we have enhanced decoherence. So one question that we're checking here is whether this can help to wash out Transplanckian features, which are usually unwelcome, and if the wave function decoheres, it might lose any effects that could be implied by these Transplanckian features. As V keeps growing, the mass term eventually dominates. We are in a situation in which we have many turning points, and we have restored coherence. So there's some kind of duality here between the Planck regime and some sub-Planckian phase, which is reminiscent of T-duality, not in the specific version, but at least in cosmological applications like spring gas cosmology. So also here may be a possibility to construct cosmological scenarios. Independently, we know that there's a variance of the system period here. So instead of directly implementing the clock through wave functions, one could try a stochastic description in which time derivatives have an additional noise term with statistical properties related to things like the variance we have here, or higher moments that could be computed just like the sigma squared. Now another difficulty is if we do actually want to use wave functions here, or we do quantum cosmology with a periodic clock, then these V's will be operators. And the system Hamiltonian should just be the standard Friedmann operator, no longer commutes with the clock Hamiltonian. So a previous treatment where we got lots of simplifications by using eigenstates of H to decouple the modes won't work anymore, because we have two non-commuting operators. So it's just impossible to have a single ordinary differential equation for each mode instead of partial differential equations. So to solve these conditions and to implement turning points, which still depend on the energy eigenvalue, numerically one has to diagonalize the phi-dependent Hamiltonian at every time step. And that's very expensive in terms of computation time. So we don't have a lot of examples yet, but a few. This one is a cosmological example expansion, small lambda, large lambda. One can see there's the same effect, that the expansion rate seems to depend on lambda. That's like this pi over 4 factor we had earlier. So would also be unobservable because it can just be included in bare parameters. But interestingly, at intermediate lambda, we get additional effects. So even though that's a system in which we should just have standard expansion cosmologically over these timescales here, it looks like the scale factor expectation value oscillates because of interference effects, because here there are only a few turning points and they change relationships, phase relationships between eigenstate contributions, which then interfere differently. So there might be something in there, depending on what scale that's happening, there might be implications on structure formation. But that's basically what we are. So just two open questions. So we haven't done about homogeneity yet in this context, so that will certainly be important. We want to check how these oscillations here could affect structure formation. A big problem is the fact that everything we do so far here in this context relies on wave functions. It's really a phase effect. We don't have a good effective theory that could give us a more direct handle on implications and see what's happening for large lambda. So that's it. I'll stop here, and there's still time if there are any more questions.
Thank you, Martin, for your talk. And I would ask the participants, those who survived, please ask questions. There are very small number of participants left, but if you have any question, then please ask. Unmute yourself and directly ask. You guys have no question? So everybody have understood everything. I will ask question later.
Yes, the test.
Yeah.
Well, we still have questions here.
Yeah. No, it was really nice because this is like, I have to say, people don't think like that, in that way. So in that way, I have to say kind of a unique talk. It is.
Yeah, problem of time. I should mention there are other groups which look at the how you can transform between different times, which I completely ignored here for this talk. Would be another long discussion. But there are a few groups, not very many, but there's been some progress in recent years.
Okay. So like, so many thanks for your time and nice lecture, I would say, because this is long rather than talk. I would upload it very soon, and we'll share the link with you.
Okay.
And like, yeah, we will discuss about this thing more, I will write to you.
Mm.
And maybe like, yeah, if I have something, we can chat sometime if you have.
Yeah, there's certainly still lots questions on this effective
Yeah,
descriptions.
yeah. Sure.
All right. Yeah, thank you again for the invitation. Everyone else for
It's my
staying
pleasure
till the
that
end.
you have managed some time, because I think you were very busy with some certain period, and then for the
Yeah, this summer actually we because students had to stay home, we actually were more busy than usual because everything kept running. It's normally summer break, but not really this year.
yeah. Okay. Have a safe stay, and
Yeah, to take care.
be healthy, and this is the main important thing we have to follow. Like everything right now is going via Zoom, but like someday we can meet like in person rather than virtually.
Yeah,
Yeah.
if airlines get running again.
Yeah.
But
Okay.
yeah, we'll see. Take care, everyone. Bye-bye.
Bye bye.